And now we're going to get into our panel discussion. So first off, we have Chris DesRoches, who is the Business Development Manager for Heating and Cooling at Swegon, North America. Swegon develops energy-efficient ventilation products and indoor climate systems aiming to optimize solutions with high people comfort and minimum life cycle costs. Chris, thank you so much for joining us today. And if you can just let me know when these need to proceed, that would be great.
Perfect. Thanks, Jay. I appreciate the invitation here to be a panelist to talk about retrofits in a little bit more detail. So for today, I'll be talking primarily about hydronic heat pumps, air-to-water heat pumps, but a lot of the different concepts that I'm going to present, a lot to squeeze into 10 minutes, but a lot of those concepts are going to apply to different types of heat pumps. Really, with any kind of heat pump, you're generating the heating or cooling at one portion of the building. You're distributing it through the building. So with VRF, as an example, that could be refrigerant going through the pipes. With hydronics, we're talking about water that's going through the pipes. And then usually, whether it's VRF or air-to-water heat pumps or an air-to-air heat pump, we have kind of terminal units where we're using that heat. So especially when it comes to retrofits, if you already have those pipes in the buildings and it's being served typically in Ontario with gas boilers, kind of you can simplify your project in a lot of ways by reusing those pipes, which comes with its own challenges. Obviously, different building types, different building usages will have some solutions that are better than others. And I'm sure, as everyone's know, with types of retrofits that you're involved in, there's going to be different pros and cons for different systems, and kind of there's no silver bullet in the HVAC world. Otherwise, none of us would have jobs. So it's really about finding the best solution for that building, which can sometimes involve a lot of different solutions. Next slide. So for a couple topics that I want to talk about today, and again, this will apply to any kind of heat pump that we're using. Some of the data is a little bit more specific to hydronic heat pumps. But really what I want to talk about is a little bit on the sizing. I get a lot of phone calls from a lot of clients and customers, consultants who are looking to do some kind of heat pump retrofit. And the first piece of data that you always have as energy managers is the sizing of the existing system, which we know for a lot of buildings 20, 30 years old can be oversized. Is that sizing correct in the first place? A lot of older hydronic systems will have higher temperatures, but does that building actually require that high temperature? And how do we kind of manage and get the best of both worlds by looking at a holistic solution? So really what I want to talk about is building load versus the heat pump capacity, and kind of some advantages with sizing for 100% or some advantages for sizing with kind of the more consistent average temperatures that we'll see. And I'll present some weather data to talk about that. And we'll talk about dual source systems, whether that's natural gas or backup electric boilers when it comes to hydronics. So I'll have some COP data to show you to kind of put that in perspective. And then I'll finish it off with just a brief comparison of an energy kilowatt hour comparison for electric resistive heat versus air-to-water heat pumps. Next slide. So this chart here is kind of showing us two things. So on the left-hand axis, we have our bin hours, which is this is the 3-year average weather data for the city of Toronto that I've downloaded from Environment Canada recently. So this goes from 2020 to the end of 2023. And for Toronto, the design temperature is about -23. And that's what a lot of buildings were designed to per the Ontario building code. Whenever you actually look at the distribution of hours that you're going to spend, you know, -23, we spend relatively few hours at -23. Between -15 and +15, we're spending Celsius, we're spending, you know, 60% of the total hours. But really what we have to think about and understand is any kind of heat pump, whether it's air-to-air heat pump, central air handling unit with heat pump integrated within it, air-to-water or VRF, as the temperature gets colder outside, we are going to see a decrease in our heat pump capacity. And I know Will's going to talk a lot about the advantages of some other types of systems, but generally the trend is, you know, your heating capacity will decrease, which is counterintuitive to what we want to achieve when we put in a heat pump system, because we need it most on the coldest days, and that's where we have kind of the lower efficiencies and the lower capacity that's available. So what I wanted to kind of illustrate here is, you know, this is an arbitrary building load heating profile, but generally speaking, at the coldest temperatures, that's where we have the most heating capacity that's required for our buildings. So we can often simplify our project. We can save on space, we can save on costs, we can save on that electrical capacity that's required to implement a heat pump in the example of using backup natural gas, to consider what's called a bivalence point. So bivalence just means you have two energy sources in the building, and you're going to switch over between the two depending on a number of factors, and that could vary. There's a couple more bullet points there, Jay. But we could determine this based off the system water temperature or the maximum leaving air temperature on an air system. So in air to water world, if our maximum supply temperature at say minus 10 degrees Celsius is 55 degrees out from the heat pump, if we look at our hydronic system and based off the heat loss of the building, we say, well, we can, still heat our building adequately at minus 10 with a 55 degrees Celsius supply, then you could simply just run an auxiliary heating source, whether it's gas or electric, below that minus 10 value and increase a higher temperature. It's important to remember too for hydronic systems, if the building's not already on an outdoor reset curve, that's one thing that should be looked at for energy savings, also improve comfort. So the limitations of the equipment would be the system water temperature requirements. I know at the start of the session, we had some questions from the audience about operating costs for gas or electricity. Feel free to reach out after the presentation. I have lots of insight on that. It's a lot to squeeze into 10 minutes, but COP could be the one factor where you're going to determine where you're going to switch over to an alternate heating source. And really that's if we're considering a hybrid system. So for example, if we determine that the minimum COP that we want to operate the heat pump at is 2.5, because that's where the economic balance point is based off that specific building's utility costs for gas and electricity, then that could be the determining factor. Okay, well, we have a COP of 2.5 at say minus 8 degrees Celsius. So below minus 8, let's run natural gas because that's more cost effective. Or it could simply be determined based off the capacity that the heat pumps can generate. So really you need to understand, and this is a little bit tricky for energy advisors without having engineering consultants who are involved. And hopefully during the questions, we can get some insight from some consultants who are maybe looking at energy modeling for building and resizing the systems, because a lot of existing systems are oversized to begin with. But in a lot of applications, chillers, most applications, you'll size the air to water heat pump based off the cooling requirement with an existing boiler, and whatever you get out of it in heating you get, and supplement the rest with an auxiliary gas boiler. If we go to the next slide, I've just kind of summarized the same weather data, but just grouping it into different buckets. So for example, this chart above is showing the same weather data, but we're looking at different water temperatures. And on the right-hand axis, we now have our heating COP. So this kind of tells us two things. The lower water temperature we can use in our system, the more efficient it's going to operate. So if we look at minus 15 with 60 degrees C water, we have a COP that's just below 2. If we're able to use 45 C at minus 15, then we could have a COP of about 2.5 roughly. And in parallel with that, we have to look at the weather data for what we want to achieve, because if we look at the average time over the last 3 years in the city of Toronto that's spent below minus 15, it's only about 50 hours, which is less than 1% of the time. So it's important to use the heat pumps when it makes sense, depending on the design and how you're going to implement it, and then use natural gas if that's your backup. You could put in a backup electric boiler as well, and you might say, well, now we only have a COP of 1 versus a COP of 2 from the heat pump. But keep in mind, you're only using after about 60 hours, and that can also provide you resilience and redundance. But really, the heat emitters that are in the building are really going to dictate the solution and the temperature that you're going to be able to operate that system at. Putting the system on an outdoor reset curve would provide some savings and allow you to find that natural balance point of supply temperature from the heat pump and capacity versus maintaining adequate indoor thermal comfort. And certainly for new builds, not sure if the audience here is used to working on new build projects, but for new builds, you have more freedom, you have less constraints to select appropriate heat emitters to pair with the system. Retrofits is where it gets challenging. So if you're looking to retrofit a hydronic building with high temperature baseboards operating at 80 degrees Celsius or 180 Fahrenheit with fin tube baseboard, there's no heat pump air source on the market that can get you those high water temperatures. You could maybe do a cascade system, which I know Will's going to talk about. Sorry, I've just seen a question come up, a reset curve. So a reset curve just means that based off the ambient temperature, we're changing our supply temperature. So, and going back to that building at 180 degree supply, when you're sizing, when the engineers are originally doing the sizing for 180 Fahrenheit, that's to provide capacity at all the indoor units throughout the building on the coldest day of -23 with 180-degree water going through the system. But if you have a milder day today, for example, where it's about 10 degrees and you could still have heating systems on, if someone in an indoor zone in a multi-unit residential building was to turn on the thermostat with that high water temperature, it would actually cause a lot of temperature swings in the suite because you'd be blasting out all this hot air. Your thermostat's going to satisfy conditions, it's going to shut off, and then a little bit later it's going to turn on again. So it's going to be cycling where it's not really providing you comfort. So outdoor reset simply means that as it gets warmer outside, we're decreasing our supply temperature to basically match the heat loss of the building, because that's all any HVAC system's trying to do, is match the heat loss of the space. So when it comes to high temperature systems, we're not necessarily going to be able to put an air source heat pump to make super high water temperatures. So we need to think about it a little bit more holistically and think about indoor comfort and kind of optimizing the existing system. The next slide is just a quick example that I wanted to kind of finish on. So just to kind of put some numbers to it and put it in perspective, this is just a very rudimentary bin hour analysis. So I'm looking at all these bin hours across all the times between -15 and +15. And I'm looking at a building load that has the same load as what the air to water heat pump capacity is. So if you look at the bottom chart in orange, we're providing all this capacity from an air to water heat pump that has a COP anywhere from 2 to 3.5. And we're comparing that to an electric boiler that always has a COP of 1. So we're assuming full load at all times, which is not a realistic assumption, because when it's a day like today in Toronto at between 10 and 15 degrees outside, we're not going to have this 100% load. So really this might represent a very, very large building, maybe an industrial building or a large office building with a lot of capacity, or maybe there's domestic hot water tied into that as well. But this is just to compare apples to apples. What does that look like? So in the blue line at the top, we see the electric boiler usage, and in the red line, we see the heat pump power usage. So the numbers come out to basically 66% reduction, which on the next slide will kind of illustrate how that's being kind of skewed to a large number, because it's really simply a function of the input power of either source that we're comparing times the load times the bin hours. So at -15 in purple, we have only 15 hours spent for an electric boiler to provide 74 kilowatts to the building. For those 15 hours, we're using a total of 1,112 kilowatt hours. For those same 15 hours at a COP of 2.5, we have the power input. So in the orange column, we see the energy use from the air to water heat pump of 542. So we can see what the savings are. So you see we have some modest savings here between -15 and about 0 degrees. And obviously, as we get from 10 to 15 degrees, we're seeing 20,000 kilowatt hours saved for each of those bin points. So the total comes out to about 2/3 reduction. So this again is just to provide a direct comparison between the two. The usage of the system and the load is going to be important. So, and again, this doesn't account for in the wintertime when the heat pump units are defrosting, whenever they're turning on, reaching the steady state versus the transient state, things like that. So detailed energy modeling needs to be done, but this is just kind of summarizing what those energy savings would look like. And a lot of manufacturers have a lot of tools to kind of help you with this, with the data from the heat pumps to see what that's going to look like long term. So that was kind of it, just to summarize, air to water heat pumps or any kind of heat pump, they provide a good balance in performance and resiliency for the building, especially with dual fuel systems with natural gas as the backup, especially if you have buildings that have maybe upgraded to condensing boilers recently that still have some lifetime in them. That could be something that's maybe left in place to use as the auxiliary heat source for those few hours where they need to run. And then once that's at the end of life, it could be replaced with an electric boiler. It depends on a lot of factors, like the capacity that's available for the building. Can you put an electric boiler on there, or are you going to cover off the majority of the savings by putting in a heat pump in lieu of an electric boiler for some savings? There's kind of two ways you could go off cost effectiveness. So if you want to do the most sensible business case, you could size it typically based off the cooling requirements if there's cooling in the building, or size it for -5, -10 if it's a heating only retrofit. If you want to optimize the electrification decarbonization, you can certainly use more heat pump capacity in the building. But you know, if you size it based off cooling and say you needed 3 units, if you wanted to meet more of the heating capacity, suppose you need 4 units, you know, for those extra 60 hours that we talked about, is it worth increasing your capital cost by a third by adding another unit to integrate it in it? So, you know, the clients are really going to dictate what their end objective is, and it's important to look holistically at it. And the heating plan is one part of it, but building envelope, looking at the HVAC system as a whole, such as decoupling ventilation for large central systems, optimizing controls as part of that, are also equally important steps, if not more important, as part of a total holistic solution. So with that, I appreciate the time to present, and looking forward to seeing some questions and hearing some experiences from the attendees.
All right, thanks, Chris. Before I move on to Will, there is one question in the Q&A about if there are any Excel tools available to share. You mentioned that a lot of the vendors or manufacturers will have these themselves, but is that something that's available?
Yeah, it's manufacturer specific. So it's important not to just look at one, like this is what I would tell people too. When you look at a catalog for any kind of heat pump, like those are usually based off AHRI, what's called standard rating conditions. So for air to water heat pumps, as an example, the COPs and capacities that are presented are based off an ambient temperature of 8 degrees, which doesn't really help you a whole lot. So Excel is one thing, it's manufacturer dependent on how much data that they're willing to provide. Certainly we'll support our customers with providing the data. But don't just go off that single rating. You need to look at a couple different rating points and see how the performance of the unit's going to be in real time, because we're going to use the heat pump at -5, -10, not just -8 at all times, and the performance is going to be different. That's going to have different implications on your system and different control considerations to keep in mind as well. So again, it's manufacturer specific, so just always be sure to ask for the data, because more data is better than just one or two points.
All right, thanks, Chris. Next up, we have Will, who's an HVAC sales engineer at HTS Engineering. HTS is a custom HVAC equipment provider focused on designing and installation of cooling heating systems for both new construction and renovation. Thank you for joining us today, Will, and I'll hand it over to you.
Yeah, thanks a lot, Jay, and thanks a lot, Chris. And you know, Chris mentioned a lot of great things there that I'm gonna kind of repeat again about, you know, make sure you're sizing correctly, understanding the load, looking at the right size in the system. You know, there's a big tendency in our industry to do like for like replacements, and that in the heat pump world that doesn't really work, and you can waste a lot of capital costs doing like for like, when doing a, you know, much smaller replacement or an undersized replacement can give you almost the same benefit for a much lower capital cost. So so it's a question, did you conduct cost savings along with life cycle between electrical boiler and heat pump? Oh, yeah, we've done some of that before. I'm sure Chris has done some of that before. Yeah, it turns out electrical boilers are really cost effective to buy, but hard to install. Yeah. So just going through this presentation here, how to decarbonize our new and existing buildings. So we're going to talk about a couple different technologies. You know, one of the things that's become really apparent in the marketplace compared to even a couple of years ago is the number of heat pumps available. I mean, people love talking about heat pumps, but there are so many different varieties of heat pumps on the marketplace. I was checking the other day, and at HTS, we sell over 100 different heat pump products. And that's going to be air to water, water to water, water to air, you know, vapor injected, non-vapor injected, it's different sources. There's so many different varieties in the marketplace. It's becoming very complicated. So that's both good and bad, that there are a lot of options out there, but you also have to understand how to go through all those options and look at what makes sense for that particular building. I'm going to talk a bit about what technology you might want to use for different applications. And then I'll also go over refrigerants as well. The refrigerant landscape is changing significantly, as we know, as kind of as part of our reduction in GHGs. There's a recognizing that refrigerants play a big part of that, that as a pound per pound or kilogram for kilogram, refrigerants have a very big global warming impact. And so there's lots of change happening in the marketplace. So that's kind of muddied the waters a little bit. And also, unfortunately, this isn't the last change. We'll have at least one more refrigerant change before we're done, maybe 2 more. So we'll see. Next slide, please. Yeah, so I just talked a bit about, you know, all the different options, just going over the toolbox. I mean, Again, for better or for worse, there are a lot of tools in our toolbox. So this is all the things that you can use: air source heat pumps, reducing your load using high efficiency energy recovery. We talk a lot about heat pumps and applying them to solve a problem, but we can also look at how do we reduce that problem? Do we put in better glass? Do we improve energy recovery? Do we, lower the water temperature like Chris talked about, low temperature heating? Wastewater is, we flush a lot of hot water down the drain. So can we reuse that hot water through a heat exchanger, through a heat pump, something else? Solar thermal heating, adiabatic humidification compared to gas, domestic water heat pumps, and of course, geothermal systems. So a lot of tools in the toolbox. It makes our jobs complicated, but it does keep us all employed. So next slide, please. Chris talked about this quite a bit. The important message about our climate is that, and for everyone here in Ontario, kind of wherever you live in Ontario, our climate is very moderate, actually. And yeah, we love to talk about design days and that the blizzard of 97 or whatever you want to think, but most of the time, and especially this winter, it's actually pretty mild out, and heat pumps tend to work really well in those more mild conditions. And I've separated here, this is in Fahrenheit, but an important bucket is at 40 to 65. So that's going to be from about 4 Celsius up to 18 Celsius. And that's a really sweet spot bucket because we have a lot of run hours there. Heat pumps don't go into defrost. And the COP, you had a question about operational costs. The COP in those ranges tends to outperform gas today because it's high COP, gas has carbon taxes, and there's no defrost. So it actually tends to work really well. So we're already seeing a lot of run hours in the marketplace where heat pumps are more cost effective from a financial perspective than a gas system. So you get into that under 40F, you get into defrost, COP suffers. Yes, it's more difficult, but there's a lot of run hours now where it makes a lot of sense. So next slide. So one of the first technology I want to talk about, and this is kind of overlooked, people get really excited about big heat pump systems and air to water and replacing that boiler, but we forget that the most common HVAC system in North America is a rooftop unit. And it turns out one of the lowest green premium is to buy a heat pump rooftop unit. So here's an example of one particular rooftop that's been changed to a heat pump. But as far as I know, almost every manufacturer now offers their rooftop units in a heat pump. And the cost premium, if you have a rooftop unit that costs $50,000, a heat pump addition to it might be $5,000. So it's a very low green premium. It tends to be, if you're sizing it for cooling, that you're not increasing electrical, you're buying the same compressors, you're buying the same electrical, same fans. So the green premium is very low. You're not increasing the install cost at all. And you get a lot of run hours. You're only buying a standard scroll compressor, but again, like Chris talked about, like I talked about, for a lot of those really warm periods where it's in the October, November, December, maybe March, April, it's mild outside, you're going to be able to run on a heat pump for a very cost-effective operational cost with a very low green premium on the install. So we've now gone to almost all air source heat pumps on our rooftops products. It just becomes so cost-effective that all of our customers are asking for this. There are still challenges for sure at the low ambient. You still want some backup heat, either gas or electric, and there are some limits on 100% outdoor air systems, but most rooftop units in the marketplace are that mixed air, doing mostly size for cooling with a gas heater. Adding the heat pump is really a slam dunk these days. Next slide. Now you get into the air to water heat pump. So the air, a lot of buildings, a lot of the commercial sector, a lot more of the complicated buildings do have a hot water distribution system. That hot water distribution system, depending on when it was built, might be 180, might be 140, it depends. But what I want to go over here is that in the heat pump marketplace, in the air to water market, we are now seeing several different levels of technology available, and of course with different performance and cost premiums. And so the most cost effective and the most readily available is the standard scroll. This works down to about 5S, so negative 15C, and can produce up to 60C, 140F. Now, it's not all at the same time. There's some limits at the lowest ambient. But for a lot of customers, this tends to be a very cost-effective option. If you're buying a chiller already, or you wanted to have a simple option to do air source heat pump, air to water, the scroll technology is quite reliable, becoming more and more readily available. And it has a low cost premium. And that will work for many customers who only want to get off the gas a little bit, not fully get off the gas, but want to take their foot off the gas or reduce their gas consumption. What we're seeing next develop the marketplace, go back, is the vapor injected scroll. So this will work down to negative 15S, that's negative 25C, I think. Still producing about 60C on the top there, but we get much better low ambient operation. So from a lot of Ontario, that's going to be full winter operation. You're going to get some heat. That might work well for a domestic water solution. You might be using it to do some heating in a building, depending on your hot water temperature. But no surprise, there's a capital cost premium to that product. And then the final one, which we can go into the next slide to talk about a bit more, is a cascade system. And so this is for, so next slide, Jay. So this is for a customer that is interested in they're getting off the gas. They want to sever that natural gas connection. They want to get off the gas. They want to be totally green, and that's great. It is possible in the marketplace, and we are happy to help customers with it, but be cautious, there is a cost premium here. What we're doing in this product concept is you have an air to water heat pump, maybe a split, maybe not, where you have the outdoor portion producing a medium temperature fluid, so 80 to 90 F, that's going to be 25 to 35 C kind of temperature range. And that fluid is then fed into another heat pump on the inside of the building. They can then produce that 170, 180, 190 F if you need it. And so this is a concept. We've seen it done in the marketplace. They had actually 100 Yonge Street, which won a lot of awards, had this exact concept in it. And that allowed them to totally get off the gas for their HVAC system for that particular building. So, and yeah, great. Thank you, Gonzalo, for that. Yeah, propane. Yeah, propane is a very attractive refrigerant. We will see how widely adopted it becomes in North America. But I tell you, if you go to a European trade show, the only thing they want to talk about is R290 as a refrigerant. They seem very committed to that. We will see what happens in North America here. And then I'm running a bit of time here, but just talking about, also the VRF world. So people think of VRF as a great option. They think about it as kind of a split system or a product that can serve a couple different spaces in your building. What we're seeing happening in the marketplace is we're really expanding the use of VRF. VRF is a very cost-effective air source heat pump. And now we are able to connect it to air handlers, domestic hot water, HVAC heating water systems, and to really seeing that expand. And then again, it comes into that vapor injected or cascade system, but great low ambient performance, readily reliable, really great retrofit solutions because of its small size and easeability. That's what they used at 100 Yonge, was a VRF to water solution. So next slide, please. I'm running a bit of time, so next slide. This is just talking a bit about ventilation solutions. So, if you have, a lot of people have makeup areas, say you have a kitchen system, you have a gas fire or a paint booth or some other gas-fired ventilation system bringing a lot of hot air in. What we're seeing as a really easy option is, hey, let's take a VRF system. We can put a coil inside of that ventilation unit, and up to your choice, how much do you want to get off the gas? You can do some heat with the VRF system as a heat pump. You can do all this, all of it. You can do kind of anywhere in between. So it's a great way to reduce greenhouse gas emissions, and there's a lot of flexibility on the install for all these existing units that are out there that maybe we can't go buy a new rooftop, maybe we don't have electrical to do the whole thing. This is a great option to do some or most of the system. So next slide, please. I talked a bit about this as a cascade system, so we can go to the next slide. Again, same thing here. We're showing just it, and we'll talk a bit about refrigerants. Next slide, please, Jay. So in the refrigerant world, I have several slides here. The refrigerant change is very complex. What's happening right now, we used to have kind of two big options, which was 134A and 410A in the marketplace. Those are being phased out due to high global warming potential. And then we're moving to, if you go to the next slide, I think I have it there. My next one, please. Next one. Next one. One more, sorry, one more, Jay. Yeah, here we go. So we previously had, two major refrigerants we're using, but somehow now we have 12 new refrigerants that we're using in the new refrigerant landscape. So it's very complex. It's still early on what's happening. We look at these GWP numbers. If we look at the very top, going from R410A to either R32 or R454B, we've definitely reduced the global warming potential. but we expect that in the future we'll have to change again. And as Gonzalo pointed out, R290 seems to be a very attractive option from there, except for the fact that it's totally flammable. So, yeah. Yeah, so that's the refrigerant one. I won't get too much more into it. It is very complicated, but if you have any questions, I'm happy to help out with that. I think that's kind of everything I had that I wanted to, yeah, running out of time that I want to talk about today. So continue on, Jay, and we can go to Belinda now.
Thanks, Will. We'll keep moving on, and there are, for Will and Chris, there are a couple of questions in the Q&A panel. If you want to, you can type answers in there as well to respond to those. So those came up during your presentations. Now I'm going to hand it over to Belinda Gilbey from BONDI Energy, co-founder, president of BONDI Energy Corporation, organization focused on retrofitting multifamily buildings with heat pumps and other energy efficiency technologies to decarbonize and electrify the built environment. Thank you so much for joining us, Belinda, and I'll hand it to you.
Thanks, Jay. And yeah, thanks everyone for joining. It's a pleasure to present. And Will and Chris did a great job sort of dialing in on more of the technical details, sizing, different types of heat pump technologies. I wanted to zoom out a little bit to about 30,000 feet and talk about our experience in this space implementing heat pump retrofits. So one, primarily, why are we talking about heat pumps to begin with? Why does it matter? Some snapshots of some case studies and different examples of different buildings that we've done, and then highlighting some of the key challenges when it comes to installing heat pumps, construction in these buildings. What are some of the challenges that we've seen, and what should you look out for when you're moving your projects forward in the future? And then lastly, sort of overview of what's the process of a project cycle from conception to breaking ground and completion. So just to start, on this slide here, decarbonization, it matters. We know that the burning of fossil fuels for space heating and hot water is a huge contributor to greenhouse gas emissions. And, as the government of Canada and the US have these aggressive net zero targets by 2050, then what do we do to solve that problem? And yes, building new buildings in the most energy efficient way, whether it's geothermal, water source, VRF, air source, that's important, but also retrofitting our existing building stock. So we sort of look at each project holistically. Where does it make sense to do it, and how do we optimize and value engineer the project so that it makes economic sense for the owner, depending on their objectives? So I won't talk about all the different types of heat pumps. I think everyone on this call is well educated on that. And like I mentioned, Will and Chris did a good job of explaining, but yeah, just those few I mentioned, geothermal, air source, really depends, but they're all very energy efficient with varying coefficient of performance. So some case study examples. This is sort of the target building profile that we work in. Any building that was built before 1990, whether it's electrically heated or gas heated with a hydronic system. So Nisbet Lodge, that's a senior care facility in Toronto. And the reason they went forward is because they wanted to add air conditioning into the suites. That's a huge thing here. Adding air conditioning into buildings that didn't previously have it, that really moves the needle for a lot of the work that we do. That was also electrically heated. So there were huge efficiency gains on the heating side, the benefit of adding air conditioning. Now that project had some unique challenges with asbestos. So building condition report said asbestos is here, A, B, and C, but it's not in this area of the building X, Y, and Z. And, we did our own assessment and testing and core drilling to make sure. But of course, what happened was when we started drilling, asbestos started coming out where it wasn't supposed to be, and even in a zone where we had tested. And the reason was the asbestos is 60 years old and it had settled, and the drilling shook it out a bit. So we had to stop, we had to abate, the hazardous material, and then pivot and adapt the scope of work to get the whole job done, which was done last summer. These other buildings, Orchard View, Argyle, and Tyndegate, again, these are electrically heated apartments that we've converted to Daikin heat pumps in all cases. So we're seeing huge energy savings. And typically what we'll do is we'll pilot one apartment or one suite for new owners that are maybe curious about what are the actual energy savings in my building, which depends on the building envelope, condition of the windows, the cladding, what's the heat loss. So we can estimate all we want, but it's really valuable to maybe do a tester and do some measurement and verification, prove the actual savings for that building, And if it makes sense, then you can scale up for the rest of the building. We're also, electrically heated buildings has historically been obviously the lowest hanging fruit, especially in Ontario, but we're seeing a big shift in the market towards fuel switching. So that's where things really get interesting. And our customers that are fuel switching their buildings are doing so because they either have a corporate mandate to decarbonize. So maybe the question isn't what's the payback, it's we need to get off of gas, what's it going to cost, and we'll pay to get it done. And then secondly, it's sort of legacy aging equipment that might be due for replacement. If you have an old boiler, especially an old atmospheric boiler, now is the time to consider making this generational shift to a fundamentally new heating and cooling system. So those are sort of the two angles that we're seeing in the market. Next slide, please. So what are the common challenges that we're seeing for executing heat pump retrofits? Number one, if we're talking fuel switching, it's building electrical capacity. So we know that our grid is probably can't support all these buildings, or definitely can't support all these buildings fuel switching on day one. It's going to be a gradual shift, and we're hoping that the grid infrastructure will be improved while this transition to more heat pumps in the market also becomes more common. But what you need to think about is there even enough capacity at the local transformer to support fuel switching? And that's part of the process. Whether it's Toronto Hydro or another utility company, you need to go to them with your plan and ask them the question, this is how much more power supply we need for this project. Is there capacity at the transformer? Are there costs associated with bringing more power to the building to energize the heat pumps? And if not, then find another building where you can do it. So sometimes there's a huge cost, sometimes there's no cost. It really depends, but you have to go and ask the question. And that's sort of part of the initial steps that we help our customers work through. System sizing, I won't get into that, but something else that we'll do is we'll upgrade the windows if that helps the heat loss, and we can lower the heat pump size. If you have single pane original windows, then you're going to be oversizing your heat pump system. Maybe you want to retrofit to a double pane or a triple pane and factor that into the whole project scope, or maybe we can add cladding to reduce that heat loss. Asbestos, I gave the example from Nisbet Lodge, but that's something to be wary of. Is it present? Is it in the popcorn ceiling? Is it in the walls? Make sure that the work is going to be done safely and make sure that it's abated if it's there. Structural, so where are the outdoor units going in the ductless or split type system? Are they going on the roof? Well, can the roof support the weight of the units? That's something you need to check off your list. Are outdoor units, if you're using a mini split type system, are they going on the balcony or the side of the building? Another thing is placing those units. You want to make sure you're placing them somewhere where they're easily accessible for maintenance and service moving forward. You don't want to put, a split type compressor unit on the third story just hanging off the wall, because you're going to need a lift anytime you need to clean it. Condensation is another big component to consider. How are you going to manage the condensation water and the defrost from the outdoor unit? Is it going to form sheets of ice underneath, which is a safety hazard for people walking around? For the indoor units, are you using condensation pumps? That's another part that can maybe break. If it's in a bedroom, it can be noisy. Is it possible to gravity drain? Do you want to tie the condensation lines into a downspout? And another thing is aesthetics of the project. How are you matching the outdoor equipment and downspouts and eaves to match the building? Where the line set's going? Aesthetics can be a concern. And it's important to note, we see in organizations there can be competing priorities where energy managers, your job is to save energy and reduce operating expenses and make the buildings more efficient. An asset manager or an investment manager is maybe interested in increasing the value of the building. And then you have a team that is going to care about how the building looks. What's the curb appeal of the building after it's done? Is this apartment going to be rentable if the installation isn't done properly or it's a mess? So there can be competing priorities or complementary priorities, but you need to manage those and understand what's the end goal for this project. What are we trying to achieve together as an organization? And then how do we value engineer this project to meet those objectives within the budget? Another big consideration is coordinating during installation. All our projects are occupied buildings, so it's a whole different ballgame than new construction, or if the unit's vacant, or single family homes, or even commercial. So if you're talking of an occupied residential building, you're managing with site staff. You have to manage the notices, make sure that your schedule is ironclad and sequenced with all the sub-trades, and you're minimizing the amount of disruption in the suite or in the space, making sure that you have contingencies for delays, which are bound to come up. You're going to have issues with access. You're going to have issues with furniture being in the way. You're going to have all types of challenges. So making sure your schedule is very detailed, and you're considering that this is an occupied space, you're going to save a lot of time and a lot of costs and a lot of delays if you plan up front. And lastly, system controls. How's it going to be optimized for performance? Are you using a BAS system? Are you just using remote controllers? Are you using a thermostat on the wall? We have some interesting solutions. We've developed a BAS system that connects all types of heat pumps to the cloud, and it doesn't work off of Wi-Fi, so it's remote and you can connect other equipment to it as well. But the goal here is to really optimize performance, prevent, behavior with the equipment, cycling compressor on and off, which can put strain on the equipment, demand response, participating in demand response programs. So a lot of cool things you can do with the controls, but if you don't consider that up front, you're not going to optimize long term. All right, and my last slide is just about the process. So step one to the final step, in the shortest time frame we've seen a project from inception to construction is about 4 to 5 months, but at the longest it can be up to 2 years. And that's especially a consideration if you have to upgrade electrical capacity to the building, because by the time you put in your application, get in the queue, and then wait for the utility company to bring more power, it could be an extra year and a half, or maybe 2 years. So step one, you want to evaluate the building, or maybe evaluate a portfolio of buildings and identify which ones are good candidates or have a strong business case to retrofit. Then you're going to enter engineering design, electrical study, mechanical study, value engineering the project, selecting your equipment. And then once you have that key piece of information, how much power do I need? Then you take that to the utility company and submit the application. But then you're typically, when you're ready to go forward and contracts are signed, then you're in the project planning phase. So you're submitting for your building permits, you're ordering the equipment. It might be, depending on the volume of units you need, it could be quick, it could be off the shelf, but if you're talking 200-300 units, there's going to be a bit of a lead time. So getting those orders in, and then working on your project planning and project management so that you're well positioned to execute on schedule and on budget when the equipment arrives and you can break ground. So all in all, the quickest is an evaluation of the building at 2 to 3 weeks. Engineering can take a couple of months, and then your upgrades and your lead time for equipment and project planning 6 to 8 weeks, and then execution. And then of course you have your time to complete. Of course, depends on the size of the building and the size of the scope. But yeah, I think that provides a good holistic outline of the process. And happy to answer any questions about the challenges we've seen on site, or any of these items on the steps of the way through. So thanks, Jay. I think that wraps up my portion of the presentation.
Great, thanks, Belinda. And yeah, now that wraps up the presentations from our panelists. It's now open to Q&A. So if you have any questions, you can open the Q&A function in the Zoom toolbar and post your questions on there, or put your hand up, and then we'll call on you and you can unmute yourself. I have a couple of questions just to start off while people are thinking about what questions they may have. One thing we heard about is that importance to understand your current situation and things like that. So if someone's looking into electrification of heating, what information would you recommend that they get before they start getting into these conversations around what type of system they're looking for? But when they're trying to figure out what might be appropriate or what buildings in their portfolio to prioritize, what type of information would you recommend that they start collecting from their facility or facilities? And I'll open this to the full panel on it.
Yeah, hey, I can, yeah.
Sorry.
Sorry, Jay, I just, my screen glitched out for a second. Would you mind repeating the question? I
Oh,
apologize.
just we talked a lot about like understanding your facilities is a really big part of helping things go smoothly and getting like the right system for your building. So I was just asking if someone's looking into electrification of their heating systems, what information would you recommend that they start collecting of the about their buildings and facilities before they start, you know, thinking about what system or having those conversations? Like, what information is it really useful for them to have when they come to you?
Yeah, so, you know, for a first pass, there's a standard set of questions that we'll ask. We want to look at your utility bills, make sure you have, you know, at least 1 to 2 years of utility bills, both electric and gas, floor plans, or architectural drawings of the building. And then if you have a mechanical inventory, so what's existing in the building, what equipment do I know I have? That's a good starting point. From there, we can help with a bit of a desk review. And then of course you'd have to go to site and get boots on the ground and really walk through the building. But those are the 3 things that you can start with: any floor plans and architectural drawings, utility bills, and a building condition report or assessment and mechanical inventory.
Will, do you have anything to add on there?
Yeah, I thought that was that's all great to hear about, and I'd also want to understand, depending on the size of equipment, so looking at how close you are to end of life, putting together a bit of a master plan of, you know, how long do you have this equipment, when are you going to be doing replacements, and then of course electrical capacity. Actually, I did it recently for electric vehicle chargers. We just walked through the building to understand, hey, how much capacity is left at the main panel. It turns out one building we had lots, the other building we did not have a lot. So understanding, hey, am I gonna need a big electrical upgrade, or is that even a possibility for this facility? Or, you know, that's good to go. This one is quite easy to upgrade. So
All right, Chris.
Yeah, yeah, those are both great suggestions. I would just kind of add, you know, in addition to an equipment list, try to understand the specific nameplate sizing. So if you have boilers, for example, try to figure out not just what the input capacity is, what the output capacity is. Try to figure out what the system was designed for versus what it's being operated at. But I would also add, talk to occupants. You know, ask occupants if they're comfortable. Like, we do a lot of work in multi-unit residential buildings. And if you're running a heating plant in the winter and tenants are overheated and they're opening their windows, well, then that's kind of an indication that sizing everything like for like is probably not the best starting place to get to, right? So maybe there's opportunities for enhancing your existing system. So I think talking with the occupants and understanding, you know, the comfort levels and some of the pain points that they're going through will help you kind of understand better how you can add value as part of the process, because a retrofit's a natural intervention point of the building, and you don't want to fall into the like for like trap.
Right. All right, great. We have a question from Chris for Belinda. What type of heat pump system did you install at the multi-res buildings with electric heat? Ductless mini splits or central heat pump systems?
Yeah, we do a lot of Daikin Aurora cold climate units. Also doing some Mitsubishi. If the building doesn't have balconies or you don't have somewhere to put an outdoor compressor, we also do a lot of Innova units, which is a through wall heat pump with no separate outdoor compressor. So those are sort of the 3 big ones for air source heat pump retrofits for electrically heated buildings.
All right, and we have another question from a participant of, what's the process for determining what your current heat load is or your available service capacity? And are there different methods to do that? I think like both of those came up in the suggestions of the information to collect, but how would they go about understanding what their actual heat load is versus what it was designed for, and checking their current load capacity?
yeah, so I can answer one of that. So with a hot water building, and it's actually not too bad. We've done this before, where we can rent a thermal meter. So you have a strap-on ultrasonic flow meter, and you can measure the flow in the pipe, and then you can measure the temperatures on the supply and return. And then if you use that and installed, or maybe you want to do a permanent install, that can give you your real heating load in that facility on an hour-by-hour basis over the whole year. So we've done that. For a non-hydronic system, it can be a bit more difficult. Maybe you have to look at run hours. If you can look at modulation of the system, depending on the output it gives you, that can give you a real heating demand that facility.
And about checking the panel capacity that's available, what would be involved in that?
Yeah, so something we've seen a lot of, the panel capacity, at least in the suite, sometimes it can be a 100 amp panel, but that doesn't mean you're getting 100 amps. It's usually, it could be fed at 60 amps. So you have to check the breaker size all the way down the chain and down to the main switch gear to really understand what's going on.
Okay,
And
so
I would
check
just add to that too, like there's diversity in the building as well, right? Like at certain times, like not all zones in the building are calling for heat at the same time. So maybe that's one way that you can expand that constraint of trying to fit everything into the existing sizing.
Okay. We have a question from Jason. If anyone has experience in hydronic in-floor systems for warehouses or manufacturing spaces, where you get like equipment or stuff anchored into the floor, and how could you do that while preventing damage to the hydronic piping?
Yeah, is that something that's just covered off with a policy? You know, this is the anchors you use, don't go deeper than that? Or is there some sort of physical protection, or how do you get around that problem?
Would that be for like in slab? Like
Yeah,
radiant in floor?
Yeah, I'm thinking just like slab on grade, and then somebody wants to put an air source heat pump, air, and all the hydronic in the floor. How can that be done in a type of setting where things are lagged or anchored to the floor? Common practice is to drill a hole right through the floor when you do anchors. Millwrights do that all the time. How do we get around that? Does anybody have any experience with that?
I mean,
I don't. I would think Will probably sells this type of equipment, but probably in-floor radiant for a facility that you know you're going to be bolting stuff frequently and moving stuff around to the floor is maybe not a good choice in the first place, unless that's your existing system. Oftentimes there's ceiling radiant panels that you can get, which would kind of do the same thing but radiate heat down.
yeah, I would agree with Chris. And the other thing I'd say is probably an X-ray, like a coring through commercial buildings is quite common, and try to avoid rebar or other piping. So you might have to, depending on how often you're doing it, you might have to be X-raying or measuring each time. So.
Okay, all right, thank you for that.
There's a question from Pradeep of, is there a cheat sheet giving MBH to electrical kilowatt required when switching for domestic hot water boilers?
If you're just talking about the sizing in this 3.412 MBH per kilowatt, so it tends to be just as simple as that. I think that's what you're asking, just the conversion.
Pradeep, if there is anything else about that, please come off mute or raise your hand or add into the chat if there's anything else. Okay, he's saying yes for that. One thing I was curious about is in your presentations, we heard a couple of examples of, you know, customers or facilities that might have competing priorities when they're coming into this decision process, you know, like operating costs versus maximizing greenhouse gas reductions, or, you know, some of those other ones, Belinda, that you mentioned. Do you have any advice on how organizations or companies can try to sort out those priorities and communicate them to a solution provider to try to get, you know, the best system or an optimal system for those needs?
Yeah, I think it's about identifying what those priorities are early on and making sure everyone's at the table having these discussions and not trying to break down silos between different parties that are involved. You know, understanding what are everyone's different goals and objectives, and just making sure that's clear and that everyone understands what those are from early on. You know, we've learned lessons in the past where maybe gone down one path of a design type, whether it was a central VRF system, and then sort of later in the design process, having to pivot and switch because of certain constraints or wanting to separately meter the project for the individual units. So anything you can flag and identify early on, making sure you identify who's involved in the decision process and what are my organizational objectives, identifying those from day one and getting everyone at the table so that it's clear and so you can move forward down the right path without wasting time.
Yeah, if I could add to that, that's a really great point. And I think in the commercial building sector, one of the biggest problems we see is that the occupied tenant space or the occupied space versus mechanical. I mean, people think of a boiler retrofit is, hey, that happens in a room that doesn't involve any occupants, and that can happen whenever I want it to, and that's fine. And you can do the same thing with heat pumps, but sometimes just doing it in the back of the house and happening off the side is easy from a tenant perspective, but working with the tenants, understanding a long-term plan, which could be 5, 10, 15 years to work on the occupied space, upgrade it, make for lower water temperatures, fix glass. You're not going to get a problem solved in 6 months, but it has a long-term plan that you can get to that solution and not interrupt your tenants in a disruptive way or occupants in a disruptive way.
Chris, was there anything you wanted to add on that about sorting out those competing priorities?
Yeah, it's a tricky one. Alignment is really important, but I can't really add too much other than what Belinda and Will have said, but it's important to understand the priorities and define that at the onset, right? Otherwise, you just go around in circles.
Right. We have a question from Edward in the chat. If anyone has experiences retrofitting K-12 schools that they might be able to share. I know we've worked with a lot of energy managers at different school boards who are in the either pursuing or working on heat pump retrofits. So any experiences on that would be great to hear about.
Yeah, I can't say we've done any K-12 schools yet. I would imagine you want to plan for construction over the summer when everyone's away on vacation. But yeah, I also imagine fresh air is probably an item that you want to address in that type of project, and fresh air circulation and heat recovery in the suites we factored in. Yeah, I'm not sure if Will or Chris have experience in that particular space.
Yeah, I'd say something similar there. You want to look at, again, depending on how far you want to go. I mean, school boards unfortunately tend to not be the wealthiest of building owners, but so I'd say looking at what's the lowest green premium. Is it a rooftop building? Can we put in rooftop or heat pump rooftops as part of our natural replacement cycle for a very low green premium? If you use unit ventilators or hot water, is there, putting in a heat pump unit ventilator or a small air to water heat pump system to start it off? Yeah, and like Belinda said, you want to make sure you're getting that stuff on order quickly, because the production of heat pumps hasn't necessarily caught up to the demand of heat pumps yet. So lead times still remain a challenge for sure.
Yeah, and I would just add, I was thinking the same thing with ventilation, because with the requirements for the code for ventilation, X CFM per kid in the classroom, that represents a huge load for the building. So that's kind of the low hanging fruit is, implement heat recovery, implement some kind of heat pump, because that's going to have a lot of run hours. That's going to run a lot of the time to offset the usage and have some immediate savings.
All right, thank you. We have another question that condensate was briefly mentioned. How big of a problem is condensate refreezing? Not in a mild year like this year, I guess. Is there a condensate management system that is being explored for systems like heat trace, or are there liability issues?
Yeah, so we haven't really had any issues with it, because we're factoring that into the scope of work from the onset, typically tying the summertime condensation, so from the indoor units into a downspout, and you wouldn't want to tie any defrost water from the outdoor unit into a downspout, because then you could have a lot of problems with the water, icicles forming and an ice block building up. You just want to make sure that the water is going somewhere where it can run off properly. So, into a garden or grass or into some drain. It's something to flag and make note of, and make sure it's incorporated into the scope of work for the installation.
I would just add, for kind of central rooftop type equipment, I've seen a lot of times, depending on the snow grade, usually the equipment needs to be mounted on stands. And I've seen custom mounted drain pans provided by the contractor kind of installed below if the equipment doesn't have its own drain pan. Some equipment from manufacturers come with their own drain pans integrated where the drain pan's heated with heat tracing, and then that's connected to a roof drain, and that line is actually heat traced as well so that you can get it to the drain without ending up with a skating rink on your roof. But it definitely is a consideration, for safety reasons to make sure that that's captured.
All right. We have another question of if you have any case studies for rooftop units installed, municipal community centers, swimming pools, ice rink facilities. Are you aware of any projects along those lines?
So I can comment on that. So I've done quite a few low carbon community centers now, and we are typically doing a hydronic system because, as you mentioned, the indoor swimming pool and the ice rink, those tend to have loads that kind of line up well and can do a lot of heat recovery between those systems. There's also the big domestic hot water load. So far the ones that I have done are all been hydronic based, and we're connecting the rooftop system into that as well, trying to develop as much heat as we can for the facility. I do not have one specifically for rooftop unit air source heat pumps.
Right. We have one from Chris saying, I like the concept of free cooling from domestic hot water heat pumps, but concerned about the control system complexity. Is there an easy way to integrate domestic hot water with the space heating system to take advantage of the free cooling?
Yes, I can comment on that again. So what I think you're talking about there is that if you use a domestic hot water heat pump in the summertime, that it's producing some type of cooling, whether that be cold air or chilled water. And so I've seen a couple different versions of that. The chilled water is quite easy to do. We put it on the incoming return chilled water line, and we're using it as a pre-cooling system. So it's chilling the chilled water, maybe doing 10, 20 tons of load, and then you have your main chiller doing the polishing at the rest. The other way I've seen it done is we had a ducted system for a boiler plant, although the ducting tends to be challenging, but it was a large boiler plant that was running in the summertime as well for a hospital. And we put the domestic hot water heat pumps in the room, and we use that to effectively air condition the boiler room and take all that waste heat out of the boiler plant and use that to produce domestic hot water instead of just having it be a hot boiler room in the summertime. So. But that one was a bit difficult there because of the airflow requirements. So.
Yeah, and just to add to that, I've seen also applications in parking garages where maybe in the summertime parking garages get quite warm. So rather than have a evaporator mounted outside, put it in the exhaust shaft for some of the smaller modular stuff to generate hot water and kind of provide a cooling effect for your parking garage as well.
And in those integrated systems with domestic hot water, do there tend to be challenges on the control side of integrating that into it, or is it relatively straightforward?
So it can be, but I think one of the things that are important that to look at when you're getting a product is that a domestic hot water heat pump, typically we think of it as controlling to the hot water side. You want to make sure that it can control to the chilled water or air side as well. And some of the newer products have that where you can say, okay, I need to make 60 degrees Celsius domestic hot water, but I don't want to make less than 6 degrees Celsius chilled water, and it will limit itself from both sides. And so that way the machine is handling the controls, and it can be implemented into a building without automation or building automation systems being connected. Because yes, you're correct, it can be complicated if the building automation team has to manage that part as well.
Okay. We have a question about wondering if you implement ground source heat exchanger integrated with heat pump for small to mid commercial, and what tend to be the challenges with that.
We've looked at it a few times. It's typically cost prohibitive or space prohibitive on a retrofit scenario, especially in a densely populated, lots of buildings place like downtown Toronto. New construction is another thing, of course. If there's no building there yet, you can dig the holes for geothermal, but retrofit, not so much, unless you have some parking space on the ground level where you can dig there. But you know, redevelopment plans, sometimes owners are planning to turn the parking lot into another building in 10 years from now. So yeah, we've looked at it, but we haven't done it.
We have a question about how big of a problem is contractors not collecting or recovering refrigerants, and how can a homeowner or other facility owner ensure that the high global warming potential refrigerants are being collected and disposed of properly?
Yeah, so it's a great question. I was trying to think of an example, but it's the same as if you send your car in to get an oil change, how do you make sure that the oil isn't dumped down the drain? You kind of have to watch. I mean, it is part of their licensing that they are required to collect it and not vent gas. And there are rules around if they do vent gas, they have to put a notification in that they did vent the gas. But you know, like anything, if you want to make sure it happened, you have to watch.
Are there any receipts that should be requested or anything like that?
Yeah, that's not a bad idea. It should be recycled back at a proper recycling facility. So you could ask for that if you wanted to.
Or for building owners, like I'm on a condo corporation, and you know, fortunately we have a water cooled chiller that leaks. So every spring when they come to tune it up, you know, they're saying, oh, we lost X amount of refrigerant over time, which is, you know, so they'll recharge it for commissioning for the spring. But that's a good indication to building owners that it's something that you need to look at and find the leak, even if it's a small leak, because with our 410A in current systems, it's so potent that, you know, if you're leaking 10 kilograms over that shutdown season, the emissions can add up quite significantly. So don't just keep you know, same as whenever you're burning lots of oil in your car, don't just keep dumping oil in it.
Right. There's a question if you have any experience with server rooms, or I guess any other internal heat generating systems that are rejecting heat all year long, and if any good examples to use that heat for either domestic hot water or other purposes in the facility, or where that might make sense.
I've seen heat recovery VRF systems be used in certain applications. You don't want to, I'm not an expert on VRF, maybe Will can answer this question better, but you don't want to have a high, you want to have a good balance for the system. You don't just want to have 2 tons cooling for 2 tons of hot air that's being generated in that room, because whenever that room needs to be cooled and there's no need for heating, you can run into issues with it. But generally with heat recovery VRF systems, we have seen some applications like that in the past.
Yeah, I think the biggest challenge we've seen is, and we talk about competing priorities, is that the IT team wants a very specific unit that only does that server room and has lots of backup and nothing else connected to it. So where we've seen some success is if you have a unit that has a dual system, so it might be a chilled water and refrigeration based system that can use both, and that allows you to do heat recovery off of it pretty easily. But then if the chilled water fails for some reason, they do have that emergency backup system, which is really critical to IT teams and their goals. So.
Right. One thing that came up that I was curious about, and that we've seen as well, is you mentioned one way to some of the information you get is like, what is the end of life? When is the existing equipment coming up for it? And we've seen a lot of advice in terms of planning around that to minimize those, you know, the incremental or the capital costs of retrofits. Do you have it? But then sometimes that equipment fails prematurely. Do you have any advice for like preparing for that situation? Because like we've seen people who are like, yeah, we're planning a heat pump, like we have got 10 years left on our boiler, and we're going to plan to electrify this building, but then the boiler fails and they end up having to do like for like, and now they've got a boiler in there with another 20 years of life on it. So do you have any advice for facilities that might be like to plan for that unexpected situation?
I would say plan to make the switch before it becomes an emergency. Don't wait for it to break. You know, these projects, they're not reactive. They're well planned in advance. You need, even if you're a year out or 2 years out, you need to know when you're planning to start, because it's be almost impossible, I think, to make that switch if the boiler just goes and you're stuck. You have to provide heat, and if it happens in January, forget about it. It's going to be a a like for like.
Yeah, I would just add like a premature failure, and I don't know how often this happens, but a premature failure that you're not expecting is probably most likely an indication of something else that's happening in the system, of system not being commissioned properly or operating properly. So for example, you see a lot of atmospheric boilers that fail because they're being operated with lower temperatures. So that's an indication that you don't need a high temperature to begin with in your building from the condensation that can occur. So something that needs to be looked at for the full picture as well.
Okay, great. I've got one other question is for organizations that may have a portfolio of buildings or multiple potential applications, maybe in like a very large facility or campus. Do you have any tips on narrowing down the best candidates for efficient electrification of heat, of like where they should, like what clues may they have or information can they get to sort of identify the priority areas to focus on first?
If it's a fuel switching project, identify where you might be able to get the capacity required from the utility. So identifying which postal codes it could work. And then you can sort of force rank different variables, which buildings have the oldest equipment coming up due for replacement the soonest. Are there certain buildings where there's a requirement to add air conditioning? So I think if it's a fuel switching project, find out first where you could even do it from the utility, and then force rank the other priorities from there. If it's an electrically heated building, then it's probably going to make sense in most cases. So then, you have to figure out, where do I have budget to do this?
Yeah, I would just add like the building type and occupancy type might be something else to look at. So for example, if you're looking at buildings like if you're a developer who has a lot of office buildings, then you're probably ventilating these buildings quite at higher rates than other types of buildings. So that might be kind of one of the first things to look at with so much ventilation, because that's something that can be immediately replaced because it's always on. Similar to lighting projects, that used to be the big focus of lighting projects because the lights were always on and it was an easy calculation. Well, ventilation's kind of like that, in my view.
We're getting close to the end. I have one last takeaway question for the three of you. If you could give people looking to retrofit efficiently, electrifying their heating system, what's the one piece of advice for their planning system that you would give them? So they're starting their planning stage for this electrifying their heat. What's the one piece of advice you want them to come away with?
Yeah, I can comment on that. I'd say that don't do a like for like replacement. Figure out how big you actually have to put a system in that's going to deal with your climate change goals. And that's likely not going to be a like for like or same size replacement. You can usually undersize significantly your heat pump system.
Yeah, I would say really consider building the right team to get it done, and consider how much project management are you expected to take in-house, or do you want to bring a team of partners, implementation consultant, supplier, to work together? And then who's going to be the project lead? Because that's one thing to consider. If you're a property manager within an organization, if you're not partnered with the right organization to do it, a lot of that work can get dumped onto your desk. So figure out who you want involved and who are the right partners to work with you to see it through to completion.
Yeah, I had kind of the same thought as Will, with not just falling into the trap of sizing like for like, but I guess I would add, don't be afraid to reinvent the wheel. And if you have a large building system that, for example, if you have a large central boiler that's making hot water for terminal units in the building and hot water for your makeup air unit and domestic hot water all tied to a central thing, don't be afraid to break that down into smaller chunks and look at them as kind of smaller subsets of the larger picture, because you basically like don't over constrain yourself from the beginning by thinking, okay, well, I got to fit something into this box. Well, maybe that's not the optimal solution. You know, maybe you can decouple with a package rooftop unit and decouple that from it so that it's independent, and you can optimize the efficiencies of your system. So kind of try to break it down into smaller chunks.
Okay, great. And we did have one more question come in saying there was a lot of talk around service capacity distribution system readiness. Do you find there's good alignment with the electrical codes and realized loads? It seems like codes are requiring larger services and equipment than actually needed. Have you looked at sites where services were increased and what the realized load versus the code load? Any thoughts?
Well, I know, yeah, we work a lot with Toronto Hydro. They've got a really great team there that has been put together more recently to help with this transition. You know, at the end of the day, if there's going to be selling more electricity, so it's more revenue for them. So there's a benefit to make this process more streamlined. And you know, Toronto Hydro typically will charge you $5,000 to take a meeting to just start the process, but you know, there is information you can find out. There's ways to work with them to optimize the design and the implementation.
Yeah, for me on our side, when we've looked at this, I would say get an electrical engineer involved. Like, it tends to be complicated, and there's a bunch of different levels of, is it the main power coming in? Is it your distribution? Is it your panel? Is it a wire size? There's many different levels you have to look at. And I'd say if you're serious about this, then get an electrical engineer involved to do even an initial study to look at it, because it can be a bit of a black box sometimes if you get into it.
All right. All right, I want to thank everyone for joining today. We just have a couple minutes left on wrapping up. I do want to highlight that there is additional support available. So we do have a strategic energy management program that is going, that we are still taking applications to launch new cohorts. So if you're interested in it, you get coaching, training, support, implementing strategic energy management best practices. You can earn performance incentives, enabling incentives. It also connects you to a great community of people who are working on this as well, and opportunities to share experiences. We have Energy Manager Support Services, who is delivering this workshop. You can access courses online, other resources, discussion forums with peers that you can connect with, as well as expert coaches. If you aren't already available on that, you can register for it with the link that Fatem has dropped in the chat. And also, Save on Energy has a new-ish training and support page where they're posting a lot of workshops, webinars, tools, and other resources, online courses as well. So please check that out. The link is in the chat. As always, we really appreciate your feedback on these sessions. So please take a moment. Fatem is going to drop the link to the feedback form in the chat now. Please click on that. I'm going to pause for just a minute now to give you time to fill that out. It just takes a minute or two, very short questions. And we do really take your feedback to heart and planning new sessions and trying to improve the quality to make sure we are meeting your needs and providing things that are useful. One other thing I'll note is through that training and support on Save on Energy, in addition to all the stuff online, there is also access to expert coaches. So through the energy management learning platform that you get from registering for Energy Manager Support Services, you can post questions. We have our expert staff, as well as a network of subject matter experts that we can rely on. So if you have any questions, please check on that. And we have one last Menti question to go before we say goodbye. And I'd like to hear what's one lesson from today that you're going to take away and incorporate into your planning for efficient electrification of heating. So I'd really like if you could share one of your key takeaways from today, one of those lessons learned that you've come away with. So if you still have Menti open on your phone or browser, you can go back to that, or you can follow the instructions at the top of the screen, or follow the link that Fatema's dropped in the chat. I'd like to thank Belinda, Will, and Chris for their time joining us today. I really appreciate it. I think it was a really great discussion, lots of really good advice for it. So thank you all for joining us. And I think it was mentioned that they're open to questions if you have any follow-ups with them. And I like seeing these key takeaways: get the right partner. The options are constantly changing. Don't do like for like. Proper heating, cooling load analysis. The air source units, the rooftop units, didn't know that those were available. So a good potential option to look into. All right, so we've got a couple minutes left. So if there are any last minute questions still available, you can do that. Otherwise, please let us know your key takeaways and have a great rest of your week.